Okay, for last 3 weeks, we studied about deformation, right? And strain. These are all about geometry, right? It comes from the geometry. So in mechanics, so very important thing first is that so geometry and deformation. This is a kinematics. And what's the other side? The other side is force and stress. Okay? Geometry, displacement, deformation, strain. Okay? These are all about kinematics. And the other side is a force and momentum and stresses. So from today, I like to lecture on force and stress. So topic today is momentum balance and stress. The strain comes from geometry, right? So now let me talk about where does the stress comes from. Okay? That's the topic. Okay, so let's draw coordinate system again. E1 defined by 3 base vector E1, E2, E3. And here we have an initial configuration. Okay, initial body defined by initial material vector, large X. And this will deform. And this is a current configuration, small X vector. In this current situation, this body subject to the external force. So external force. So there are two different external forces. First one is a body force. And second one, surface force. So, surface force, you remember when we define the surface, we first defined its normal vector, right? Surface is defined by its normal vector. So, let's say we have a normal vector n, and this is a surface force. Let's say surface force is T. Actually, this is actually not the force. Its name is traction. So this is force per unit area. So let's say surface force F S equal T dA. Fs is a small surface force applied to small area, dA. And body force, Fb, equal, let's say just F, and d omega t. So body force is the other name of body force is volume force. So volume force is applied in the volume. This is F. So in current body, this is a current body, there are two external forces. One is applied in the outer surface. So surface. And the other force, body force, is applied inside of the body, all the body. Okay? So let's say, okay, so so that volume force is applied in whole body. So what kind of volume force you can have? So for example, okay, so yeah, let's say here we have some floating structure here. Okay, what kind of external force is applied in this floating structure? Okay, gravity. Yeah, very nice. So, is it applied to the surface or in the body? Right, gravity. It's due to the gravity constant G. So gravity equal minus G and rho d omega t. Okay, E G direction. So let's say this is a EG. So gravity force is acting in the minus G direction. Okay, downward direction. And which force? Excuse me? Water pressure? Okay. So water pressure. So water pressure will be applied here. Water pressure will be applied. So something like this. This water pressure is applied. Pressure. Is that surface force or gravity force? So volume force. Pressure. Is this surface or this is surface force? So let's say N is this direction. Then N and magnitude is let's say minus G. Minus Z and G and dA. Water pressure is something like this. Is a surface force. So some of the water pressure give us buoyancy, right? And actually there are also, air pressure here. So air pressure and water pressure and gravity is applied in this floating structure. So water pressure and air pressure is an example of surface force, and gravity is body force. So for example, if this body is moving, then we can have one more additional force. Inertia, right? Inertia equal minus A, okay, and rho omega t. This is a mass. So inertia force is acting if this body is moving, right? So inertia force is also body force. Okay. So now you understand what kind of force we can have, right? Okay, if I pull my skin like this. Is this surface force or body force? Body force? Because this is my body. No, this is surface force, okay? Okay, momentum balance. Okay, let me talk about momentum balance. This is nothing but generalized Newton's law. You know Newton's law, right? F equal ma. This is Newton's law, right? So if we generalize this simple Newton's law, we can have a momentum balance. So momentum balance is a superset of this epsilon ma, F equal ma, okay? So there are two momentum balance. So first one is a linear momentum balance. Linear momentum balance. What's the linear momentum? M I V I. This is a linear momentum. Mass, velocity. Okay? And I mean some particle. Mi is a mass of some particle. So here I have a particle and it's the mass is m, and it's moving with the speed vi. And its linear momentum is mv. And of course, we need to have some coordinate system. This is a linear momentum. And then the other momentum is angular momentum. Angular momentum. So, sorry, I need to delete balance. So this is a linear moment, angular moment, x, scalar product, vector product, mi, vi. This is the angular momentum. So each position is x. Okay? If I multiply its position, okay, with the vector product, we can calculate angular momentum, linear moment. So there are two momentum, linear momentum, angular momentum. Okay. So first of all, let's okay, over there, m mass, v velocity, and x position. Let's consider discrete system. Discrete system means we have many particles, each have a mass. Okay, so something like that. This is a xi, mi, and this is moving vi. Okay, something like that. So we have many particles. This is discrete system. You can think this is all the, ball. Okay, ball is flying or moving, which has a mass. I equal 1 to n d t d m I b I equal I equal 1 to n f I external. The name of this equation is linear momentum balance. Linear momentum balance. Okay, and I and dt d x vi equal it's angular momentum balance. So for all the particle or all the body, so for example, you know the solar system, we have sun, moon, and Earth and Saturn, right? They are moving. But this linear momentum of all that, planet, is these two equations is a hold. Okay, so both are the Newton's law. Here, external force I equal, so there is no surface force. This is the external force. So here some external force is applied. Fi external. So note, for example, if number of the particle is 1, then this equation, first equation become dt d m 1 b1 equal f I 1, right? And mass is constant. Mass is constant means mass doesn't change about time. Then this equation just become m1 dt db1 equal f external. Watch this. This is AI. So F equal MA, right? This is just F equal MA. Okay. Okay. This is a very important law. Generalized Newton's law, so momentum balance. So you should remember there are two momentum balance, linear momentum balance and angular momentum balance. Okay, so Okay, so now let me talk about continuous system. Because we have a body, instead of a lot of small particles. Actually, if the body is composed by that lot of particles, right? That's very simple concept. So, in discrete system, we have a position of a particle I and mass of particle I and velocity of particle I, external force of particle I, right? And continuous system. Okay. Position just become x, right? And how about the mass? Mass become rho. This is a density and d omega t. Very small current volume. And how about the velocity? Okay, velocity just become velocity without I. External force. F B plus Fs. Body force and surface force. In discrete system, okay, there is we cannot, there is no difference between body force and surface force because that particle is very small and it's a rigid body. But continuous system, we can have two types of force. So, because of this relation, we can rewrite. Also, that summation become integral, right? Then linear momentum balance for continuous system, linear momentum balance. So over there, dt, d, and integral about the whole volume, and here over there m. So we need to have rho and velocity v and d omega t equal and omega t volume force F d omega t plus and okay, so surface force omega t and t dA. So here this become omega t F d omega t plus t dA. Right? This means surface. Here I have a partial, and this is volume. This means surface. Surface of volume omega t. This is a linear momentum balance. And how about the angular momentum balance? Is it similar? Okay. dt d and integral x rho b d omega t dA, something like this. This is angular momentum balance for continuous system. So let's look at the first equation over here. So if we can move this to the inside, if the density doesn't change about time, then we can have equation from here, omega t rho dt dB. This means, what's this? Acceleration. So I like to put just gamma. Gamma and gamma equal dt dB d, and here we have also body force, right? So this is also about volume integral F and d omega t equal t dA. Same thing, right? Angular momentum balance, and we can do exactly the same thing for angular momentum balance. Omega t x rho gamma minus f d omega t equal omega t dA. Okay. The name of this equation is also dynamic resultant theorem. This is a dynamic moment theorem. So both equations should be satisfied for all the material body. Okay, even your body and here the desk and solar system. For static and dynamic problem, this should be specified. This is just Newton's law, extension of Newton's law. Okay. So both are very important things. In undergraduate school, you know the equation in statics, F sum of fx equals 0. You remember? Sum of fy equals 0, sum of fg equals 0. For static problems. This is same thing. This is dynamically resultant theorem when the body doesn't have a motion. For some fixed body, we use this equation to solve. And also, sum of moment x equals 0 about x-axis, y-axis, g-axis is 0. Okay? This is a moment theorem. Same thing. Okay? So actually this equation comes from here, that equation comes from over there. Okay, right? But these are the origin. Okay? But in undergraduate school, just you should memorize, right? Because the teachers say this is a law and rule, so you need to remember. So, and okay, same thing, all the same thing. Okay. Any question? Yeah, just equation looks a little bit complicated. So once you understand, this is nothing, right? Just look at the older term and then think physically. Here, rho density, v velocity. This is a volume. So rho volume density multiply volume give us mass, and this is a time derivative about v, m, a. Acceleration, this is a force. Here, this is body force. Okay? To calculate the whole body force, we need to integrate about the volume. This is volume integral. How about this? Surface force at some point of the surface. So if we wanted to calculate all the sum of the all surface force, we need to integrate about surface, right? That's it. And then linear momentum balance is just there is x, okay? This x mean, momentum arm. When we calculate the moment, right? We need to have some moment arm, right? This is the arm, moment arm. Okay? Okay. Yeah, let me drive the action-reaction law. Action-reaction law. This is also Newton's law. Okay? We can drive the action-reaction law. let's consider a cylinder here. This is a cylinder. Okay, which have length h, and cylinder have three surface, right? Three surface. Left hand side, right hand side, and circumferential side. And the length direction is this is direction n, and the other direction minus n. Okay, and let's say it has a the area of that circular panel is A, and here cylinder side is let's say this is how can I say, T. Okay, I don't want to use just let's say omega t partial omega t dash, and this is R direction, E R direction. Okay, and in this body we have a external surface force. So here some surface force is applied, T. Okay, here also some surface force is applied, T. So surface force is depend on the surface, right? So this T traction, so it's a function of n, minus n. So we have a three surface. Here A, here also A, here partial omega t, three surface. And then in this equation I like to apply this dynamic resultant theorem. Then equation become whole volume omega t rho gamma t minus f dA d omega t equal we have a three surface. In this case we have a three surface, and also in this cylindrical surface some traction is also applied, T E R. So we have 3 T n plus T minus n d A plus partial omega t T E R d A, right? So left hand side is a volume force, body force. Right hand side is surface force. So right hand side we have a three traction corresponding to three surface, right? And then I'm gonna limit. I'm gonna H go to the 0. Okay, cylinder collapse. Cylinder will collapse. Then what happened? Okay, volume becomes 0, right? If the H goes to 0, then volume goes to 0. So this term goes to 0, and also this term go to 0. So finally we have equation a t n plus t n dA equal 0. So inside of this term equal 0. So finally we have t n plus t minus n equal 0, or t n equal minus t. Okay, t minus n equal minus t n. What does that mean? What's the physical meaning of that? So cylinder is almost collapsed, something like that. Something like that. So here are the poles. This is minus n. This is n. Okay, so, and here poles t. This is t. And this is a tn minus t n minus n. This means this pulse and this pulse has the same magnitude but opposite direction. Oh, case is something like that. So here, let's consider this surface. I push this surface with some force and with some direction. Then this wall also pushing me with the same magnitude of force and opposite direction. So opposite direction means I push this wall in this direction. This wall pushes me in against me. Okay, so something like that. Case is something like that. I am push the right hand, push left hand. If the left hand doesn't move, it should also push the left hand. Okay. Okay, this is a action reaction. No, this is the normal contact force. So okay, so